In the name of God. My work is about virtual machine consolidation using SLA-aware genetic algorithm placement for data centers with non-stationary workloads. I will talk about virtual machine consolidation problem in this presentation. Then I will review related works in short. Then the system model will be presented, dynamic workloads characteristics will be introduced, and finally the results will be presented. Performance of applications running in cloud environment is important, but nowadays power consumption has become very important as well. This is because of the high electricity bills, additional requirements for cooling system, and etc. Observation of resource utilization by virtual machines in cloud data centers show that most running VMs only operate on a small part of the maximum requested resources. We can use live migration based on the current resource demand by VMs to place them on a reduced number of active physical machines. This is called VM consolidation. As defined, VM consolidation reduces the overall energy consumption in cloud data centers. It is important to note that reducing the number of active VMs comes with the higher risk of low quality of service than what it is stated in service level agreement. That is, it may lead to SLA violations. Therefore, it is important to present SLA-aware placement solutions. Generally, a set of independent long-running applications of different types share the computing resources in cloud data centers. Each application generates time-varying utilization and is deployed on a VM. When we use VM consolidation, overload and underload conditions may happen. Actual overload is when the requested resources on a physical host are more than its capacity. It leads to performance degradation of applications. That is, SLA will be violated in this condition. On the other hand, if a host is considered to be underloaded, all its running VMs can be migrated out from it, and the host can be switched off or switched to low power mode. Therefore, there is a trade-off between energy consumption and SLA violation. The main goal of VM consolidation is to minimize energy consumption while satisfying quality of service constraints. Based on the things discussed, the consolidation problem can be summarized as follows. Determine what time, which VMs, and where VMs should be migrated to minimize the total cost in the system. The dynamic VM consolidation problem can be divided into 4 sub-problems. Host overload detection, that is, deciding if a host is considered to be overloaded so that some VMs should be migrated from it to other active or reactivated hosts to avoid violating the quality of service requirements. Host underload detection, that is, deciding if a host is considered to be underloaded so that all VMs should be migrated from it and the host should be switched to a low power mode. VM selection, that is, selecting VMs to migrate from an overloaded host. VM placement. This subproblem indicates the new places of the migrating VMs in case of overload detection and underload detection. The main costs in consolidation problem include energy consumption of computing nodes and SLA violation due to overload. That is, the provider should pay the penalty for SLA violation. There are also other costs costs such as migrations and energy consumption of cooling systems. There are many works done in the field of VM consolidation. However, the current work is inspired from a previous work which considers workloads as stochastic processes. However, that work uses a heuristic method for VM placement problem, while meta-heuristic approaches are more efficient in finding optimal solutions. The mentioned work uses a static sliding window method to deal with non-stationary workloads, which is not compatible with unknown workloads. We present a workload adaptive approach to deal with non-stationary workloads. The system model is shown in this figure. The system consists of heterogeneous VMs and PMs. Virtual machine monitor on each host operates with data center manager to perform the consolidation problem. The main idea of workload analysis is based on the central limit theorem. Based on the CLT theorem, the workload distribution can be considered to be normal. Real-world workload data are non-stationary. Using a fixed length sliding window may lead to not optimal solution for the best length of sliding window. A novel algorithm is proposed which is used to find the current stationary workload trace. Two sample student t-tests can be used to find whether the means of two sets of observation are significantly different. The algorithm employs two sample student t-tests with unequal sample size and unequal variances to detect the significant changes in the workloads on PMs. Here we present the algorithm to find the length of the sliding window dynamically. The algorithm employs two sample t-tests to find the target window length. The optimization problem can be defined as minimizing the number of active hosts using the workload trace exported from previous algorithm while keeping the probability of overloading below a predefined threshold. The threshold makes the algorithm as an SLA-aware solution. For overload detection, if the overload probability becomes greater than the predefined threshold, we consider the host as overloaded. Also, a local regression method is also used for short-term utilization prediction. For underload detection, the list of the hosts that are not considered as overloaded is given to the placement algorithm to find the PMs can be considered as underloaded. Main performance metrics are OTF, SLAV, and ESV, which are explained in the paper. Results show that our proposed algorithm outperforms the benchmark solutions in OTF metrics. This proves the validity of our solution in reducing SLA violations. It is also seen that our approach has acceptable number of migrations when compared with benchmark algorithms. Total SLA violation, which is evaluated by SLAV metric, has reduced in our approach, while the proposed solution has the second rank in energy consumption. Finally, to evaluate the overall performance of our proposed system, the ESV metric is used. The results show that our approach works best when we consider both energy consumption and SLA violation simultaneously. In this paper, we presented a workload adaptive server consolidation approach which is energy efficient and also has a high quality of service. An approach for modeling the utilizations of VMs and PMs based on the variations was presented as well. A new VM placement algorithm was proposed which succeeded in reducing the total energy consumption in the system while avoiding SLA violations. The performance of our proposed algorithm were evaluated by means of CloudSim simulation toolkit and real workload data of PlantLab. The performance of the system has improved in SLA violations, ESV, and number of migrations due to overload. For future work, we want to further improve the proposed system by finding solutions for more energy efficient VM placement while keeping the SLA violations as low as possible. Thank you very much.